Hey, welcome! All around us, the world is constantly communicating. Our modern technology, everything from your phone to advanced medical scanners, it all works because it understands this hidden language that's encoded in, well, everything. So let's learn how to see what's hidden in plain sight. And that's really the big question for today, isn't it? How do we take something that's fuzzy or noisy or maybe even totally invisible and somehow make it crystal clear? The answer you'll see is actually way more straightforward than you might think. Check this out. This is a perfect example. On the left, you've got this aerial photo that's just completely useless, totally washed out by clouds. But then, look at the right. It's the same image, but now a whole network of roads is visible. So how on earth is that possible? It's not magic, I promise. It's all about understanding the language of information. And that language is the language of signals. The secret to transforming that photo, and honestly, so much more, is all rooted in this one fundamental concept. So what exactly is a signal? Okay, so to break it down, a signal is really just any way to carry information. Just think of it as some kind of value that changes. It could be the temperature changing from morning to night, or it could be the brightness of a single pixel changing as you move across an image. And this idea is, well, it's everywhere. A signal can be that squiggly line representing the sound pressure from my voice hitting a microphone, or it can be the different shades of gray in a picture. It's like the basic alphabet we use to describe and record the world. Now, this language, it kind of has two main dialects, or two fundamental types. And if we want to understand how we actually manipulate information, we've got to know the difference between what we call continuous and discrete signals. So here's the deal. It really just boils down to this. A continuous signal is a smooth, unbroken flow of information. It's defined at every single instant. Think of it like a ramp. A discrete signal, on the other hand, that's more like a staircase. It's just a series of individual snapshots defined only at very specific points in time. This wavy line here is a perfect way to picture a continuous signal. It has a value at every single point in time. There are no gaps. In fact, the sound of my voice reaching your ears right this second, that's a continuous signal. Okay, so what about a discrete signal in the real world? This chart of the Dow Jones Stock Index is perfect. We don't have a value for every single nanosecond, right? We have one measurement once per week. It's a sequence of separate, individual data points. So how do we get from the smooth, continuous world to the discrete world of computers? Well, this, right here, is the key. It's called the sampling process. This is how all our digital tech listens to the analog world. It takes little snapshots of a continuous signal at regular intervals, and that converts it into a discrete signal that computers can actually work with. Literally every digital song you've ever heard went through this process. Okay, so we've got our signals. That's our raw information. But how do we actually do anything with them? Well, for that, we need the second hero of our story, systems. The easiest way to think of a system is like a recipe that transforms information. And this simple diagram, it basically tells the whole story. You've got an input signal, your X, going into this box we're calling a system. And what comes out the other side is a brand new modified output signal, Y. The system is just the process in the middle that does all the work. Let's just stick with that recipe idea for a second because it works perfectly. Your input signal, let's say it's a really noisy, old audio recording, those are your raw ingredients. The system is the recipe, the set of instructions you follow to clean it up. And the output, that's your finished dish, a beautiful, crystal clear recording. All right, it is time to connect the dots. We have signals, that's the information, and we have systems, those are the recipes to process it. So let's see what happens when we put them together and solve those mysteries we started with. Remember that choppy stock market chart? It's really noisy, right? Lots of little ups and downs that make it hard to see the big picture. But if we apply a filtering system, our recipe, we can smooth out all that noise. Just look at the bottom chart. The system took that noisy input and created an output that clearly shows the real long-term trend. Pretty cool. And now for the main event. Here it is again, our cloudy photograph. The image itself is just a two-dimensional signal, so we apply a specially designed enhancement system to it. The recipe for this system is designed specifically to ignore the clouds and boost the details of whatever is underneath. And the result? The hidden information, those roads, is revealed. You see, it was there the whole time. This whole framework of signals and systems, it isn't just a neat trick for a few problems here and there. It is, and I'm not exaggerating, one of the fundamental pillars of modern science and technology. It has a super rich history that has led directly to the world we all live in today.
And this all builds on the work of absolute giants, people like Joseph Fourier here. He developed some of the core mathematical tools, like the famous Fourier transform, that allow engineers and scientists to break signals down and design the incredibly powerful systems we rely on every single day.
And when I say this stuff is everywhere, I mean it. You know those cleaned up historical audio recordings? Signals and systems. The MRI machine that lets a doctor see inside your body without ever making a cut? You guessed it, signals and systems. The photo filters on your phone, your noise-canceling headphones, the very Wi-Fi or cell signal that's bringing this to you right now, it is all built on this exact same framework. So really, it all comes down to this. The world is speaking in signals. The information is all around us all the time. Our big challenge and our greatest opportunity is to just build the right systems to listen. Thinking this way just opens up a whole universe of possibilities. We've already learned to see through clouds, to hear through static, and to look inside the human body. And that just leaves us with one really exciting question. Now that we know the language, what will we learn to hear next?